This is 6.4.22. We'll introduce circular shifting. Now, let us have a signal that is 6 samples long and it is 0 outside this 0 to 5 sample index. Now, we're going to periodically extend it. That means we'll basically repeat this. And now we have x underscore n to say that this is a n sample periodic sequence. Now when we advance by 2 samples, we're going to shift right. Basically the new sequence is xn plus 2, so we are going to shift, left I mean. So this sequence is going to be shifted left. So I'll draw you the original sequence. You realize that these 2 samples are shifted here. So circular shifting basically will cause its periodic sequence to be shifted into the values of the current window. And this effect is not something that we want later on when we are performing convolution. So I repeat, circular shifting basically means that when we have a periodic sequence and we are shifting the original sequence either left or onto the right, the periodic extension of the sequence will be shifted into the current n sample that we are observing. And this is called circular shifting, as in we think of all these things outside that window to be shifting into what we can see. So you can use this following symbol, n modulo n, to get the values that will be shifted in, the sequence that will be shifted in. So this n modulo n, or this notation over here, is represented by these 3 conditions. If little n is between the n sample window, then nothing changes. But once n is greater than the big N, then what happens is that we are going to change the index to be n minus n, and if it is less than 0, it will be n plus n to get the value of the sequence that we are interested in. And why is this important? It is because circular shifting affects convolution. Remember that the convolution is written by this star with a circle line. In this particular case, we are talking about circular convolution here. And here, the little tilde is to say that these signals are periodic. So when we have periodic sequences and we perform circular convolution on them, will result in circular convolution. Now, so what happened is that this is the equation that shows the normal convolution. However, because these guys are periodic, this n minus m have to be calculated using this notation here for the n modulo n. So this is n modulo big N, and this is from this equation over here. To interpret, you should look at this diagram to understand that when we are shifting out by delay or advance, then the extension is being shifted into what we can see for this n sample. That's what we're talking about. So what's the big deal? Well, the take-home message is this. This convolution equation uses h, and h now behaves like in circular shifting case. And this differs from linear convolution, because in linear convolution, we want a linear shift. We're not interested in a circular shift. We do not want things to be shifted in the next period to be shifted in, as in a circular shifting operation. So when this happens, we call the linear convolution, when it is being affected by this phenomena, we call it the circular convolution. Now, why would this occur? And this primarily occur because in DFT, when we're using DFT to perform convolution in the frequency domain, DFT is actually behaving like DTFS, which is behaving as if the sequences that we are dealing with are periodic. So we inadvertently realizes or uses circular convolution when we are using DFT, but this is not what we want. So how do we overcome it? It's something called zero padding. We'll explain zero padding in the next few slides. Thank you.